We want to spend a little time here talking about the differences between C++ and Java in terms of how we go from source code to creation of an executable and running. We want to talk a little bit about the portability, as Java is defined to be or described to be very portable. We want to kind of get an understanding of what that is. So let's get started here. So let's start with C++, because probably the language you did in Intro to Programming course. Suppose we want to take an application and we want to be able to run that application on a Windows machine or a Mac machine. So we start with the source code, and the basic flow is to do a first step of compile. And from the Windows side, we need a Windows compiler, something that runs on a Windows machine, and it's going to compile into object code, and that object code is going to be Windows specific. On the Mac side, we need a compiler that runs in the OS X environment and knows how to generate object code for an OS X environment. After the compilation stage is done, we go through a linking phase to bring the executables together, and similar to compilation, we have the Windows linker has to be something that can run on a Windows machine and know how to link Windows object code into an executable that can run on a Windows machine. And on the other side, we need, in order to get an executable for the OS X environment, we need a linker that can run in OS X, and it has to know how to pull together those object code files into something that can execute. In terms of sharing, the best we have is being able to share all our source code, so we could maintain a single repository of code, and when time comes we could just compile it into and link it into an executable that can run on our target platform. But this is about the best we can do. So let's switch our attention to two Windows machines. So given a set of source code, how can we get an application that can run on both? Well, if we go towards one machine, let's assume we have a compiler, we can compile the source code into a collection of object files. We can take those object files and link them together in executable. Now, assuming that our application has only used C++ core libraries, and let's assume we're running on similar operating systems here, we can just take that executable file, copy it over to the second machine, and run it there. But what else could we do? Well, to get something to run on that second machine, we could actually take the source code, and assuming we have a compiler and linker, we can just compile it to object code and link it into an executable. Since we're using only the core libraries, we could also compile the source code on one machine to get the object files. We could share all those object files onto the second machine and then link on the second machine to an executable and run. So in this sense, we have portability of source code and we have portability of object code when we're running on the same platform with the same, using just the C++ core libraries. Of course, there might be more involved. We might have source code that has dependencies on static libraries. Static libraries are ones that are contained in that are in object code, and the object code is all linked together into a single executable, so the executable is standalone. So going down the one side, we could, on machine one on the left, we can compile into object code. Machine one has the object code available for these third-party libraries. Link it all together and get an executable. We could take that executable and move it over to the second machine and run it. That would be fine, because the executable is self-contained. On the other hand, if we tried to go the second path, if we got all the object code from compilation, or if we shared the object code from one machine to the other, if there were other libraries that were involved, OBJ files, we would have to link them. We wouldn't be able to link them together because we wouldn't have all the parts. So let's take a moment and see if we can exemplify that using using an example on Windows with a Visual Studio compiler.
The first thing we want to do is to demonstrate the build process as being composed of two phases. There's the compile phase and then the link phase. So if you're using Visual Studio in the IDE, when you write your code, you go through some dialogues, you click build, and your program seems to build, and then you can run it. So we're going to do it via the command line so we can see a little bit more of what's going on. So the first thing we're going to do, we have our single hello world program here, fairly simple. We're going to compile, then we're going to link, and then we can run. So the first stage is to do the compilation. Don't worry too much about the syntax here. We're more interested in the outcome. Okay, so we compile, we see we got a .obj file, and now we link, and what we do is we link the object code into an executable. There's a little bit more going behind the scenes here, but for our purposes this is going to work. We have our hello.exe that gets formed, and now we can run. Okay. That's all well and good. Normally we don't have our systems be composed of a single file. As things are complex, we need to break it up into parts to be more manageable. So what we'll do is create a little library called hello library, and we'll farm out the details of trying to write something to the screen to that library. So we create this hello library. There's two files, a .h and a .cpp. The .h has the what's available. The .cpp is the how it's implemented. So we see that this library has a function called say hello, and this is how it's implemented. It just has a simple cout statement saying hello static world. So we're going to replace our actual manually writing something out to call the function say hello, but in order to get access to it we have to include the header file so we can see it. Okay, so .h. Okay, so the first thing we can try to do what we did before. We can now, and so we can see what's going on, I will delete these. Okay, so what we'll do is first compile hello, like we did before. Okay, we get the object code file, no problem there. Basically, it compiles this file and says, okay, say hello, finds it defined here, it's good to go. And then we try to link it. And what we run into is a problem. It's saying say hello unresolved symbol. Basically what it means is it's looking for the implementation of or the object code associated to the say hello function, but it can't find it. Not too surprising because we never compiled hello library, which has the details. So we'll do that compilation now. And we get hello library.obj, and now we have all the object code we need, so we can link those together. So link hello.obj with hello library.obj. Okay, now we get our hello.exe and we can run. And we see hello static world, which is what was implemented in hello library. Of course, we also want to talk or see you know, that we can move from one machine to another. Of course, if we had all the source code on our other machine, we'd be able to do the compilation and build our compilation and link no problem because we had everything available. But it turns out we can also, if you notice, our link was done just by having the object code. So the two stages say compile gets to the object code, and then once we have the object code, we link it together. So we could take our CPP file, our hello.cpp, our header file, so we can see the library, and the obj file for the library, the implementation, or the object code for it. We can move that to our machine 2. Okay, we're just using a file here. And then we can go in and do the compilation. Alright, we'll do the compilation of hello to get the object code. So that'd be like us writing our little application on another machine, and we want to use the library. And now we have the object code available, so we can just do the link of the two of them together. Okay, and then we can run. And we see that we are now running on machine 2.
Alright, so we saw an example where we took the application code, that was our hello.cpp, and the third-party object library, which was the hello library, to the second machine. We didn't have the source code for the hello library.cpp. We didn't have that to be able to compile it, but we were able to link our little application with the object code from the library to get an executable. So this is all done at the link stage, but it's also possible to have a situation where you have built the executable, and executable depends on a third-party shared library. On the Windows machines, this would be a DLL, and perhaps at some point you've tried to run an application and you've got an error saying a certain DLL is not available. This is the situation here. So we're able to build our application, and there are hooks in the application that identify the need for this third-party library. So when the executable runs, the environment knows to make that connection, and does so, which enables the application to run. If you copy that executable over to another machine, and that machine doesn't have this third-party library, doesn't have this DLL, then it's not going to be able to run. So let's take a moment and see if we can exemplify that.
So we saw how static libraries worked in the sense that we had multiple CPP files, we compiled them into a collection of object files, and then we linked the object files together to create an executable. So now I want to just take a quick look at a dynamic library in the Windows environment that's a DLL. So we're going to create a simple DLL and see how that works. But basically the structure is still the same. On our hello.cpp we have a main, and we're just invoking say hello. In this case we changed the library, so rather than using the static version we're using a dynamic version. The implementation of the dynamic version looks the same. It's just a simple cout statement. The header file is pretty much the same, with the exception of the special syntax that is just enabling the DL or the DLL. But in terms of compilation, we pretty much are doing the same thing. The only difference is we have, since there's going to be a dependency of the CPP, hello CPP on the dynamic library, there's a little bit some work to be done. We're just going to simplify the steps, and we'll start by just compiling the dynamic library into a DLL, and then we will just build, rather than making multi-stage, we'll just build the main here into an executable. Again, don't worry too much about the syntax, but we're going to first take our dynamic hello library and create a DLL out of that. Alright, if you notice over here when we did that compilation, we got a lot of artifacts. Really the ones we're interested in are the .lib file and the .dll file. In fact, we can get rid of the other ones. But for now we're just going to, the .lib file is, we'll see, is that is what's being pulled in when we compile it or when we build the hello CPP. It's sort of taking the place of the .obj file from the previous example. So anyway, we have that together. Now what we're going to do is do our build of hello.cpp, and we have to indicate that we're linking it to this lib file here. So dynamic lib. Alright, so now we see our hello.obj and our hello.exe, and we can run it. Okay, and now if we wanted to, we can, if we were to pass this hello.exe file off to another machine, which is kind of what we'll do now, is we'll take hello.exe, let's say we want to hand that off, so the equivalent would be copying, and then we'll go into machine 2, so let me delete these from a previous thing. Okay, we'll paste in here hello.exe. We'll transition over to that machine, so cd to machine 2, and we'll try to run hello, and we get an error saying the DLL is missing. I'm sure most of you encountered this at some point. So what we need to do is to go back and copy the DLL file. In other words, make sure that DLL file is available on this other machine. That's what we're simulating here. So now with the DLL available, if we type hello, try to run it, it runs just fine.
Alright, so hopefully you have a sense of what it means to run an application without a DLL, and then once we put it in there, we didn't do any recompilation or relinking, and we're able to run the executable sort of on this this second machine. Now let's move on to Java and see how it differs. So, as with C++, as we might expect, we have to write some source code. That code is contained in .java files. And then we want to compile. If we're on a Windows machine, we need a compiler that can run on a Windows machine. If we're on a Mac, we need to have a compiler that can run on a Mac. And when we do this, we end up getting generating these .class files. And inside those .class files is what we refer to as Java bytecode, sort of the very similar to the object code. What's interesting, though, is that the Windows compiler and the OS X compiler, they both generate the same .class files. So regardless of the platform you're on, when you compile your Java code, you're going to get the same Java bytecode. Once you have the Java bytecode, what you need is virtual machines, and if you have a virtual machine that can run on a Windows or one that runs on Mac or Linux or whatever you would like, once you have those virtual machines, you can point the virtual machine to run these class files. The class files get loaded into the virtual machine and executed. So what we have is the class files certainly the Java files are portable, but the class files themselves are portable and move from machine to machine. That's kind of the purpose of Java. So we talk about Java being highly portable. It means that we can write the code once on some machine, we compile it, and those .class files become usable on any machine. Much like what we saw with the static libraries, if we are in Java and we want to be able to have an application run, we have to have all the .class files. So if we only copied some of our class files from the Windows machine to the Mac machine, we wouldn't be able to run on the Mac machine. No, you have to have all the .class files related to your application for your application to run. That shouldn't be too surprising. What other issues can you run into is we're assuming in this picture that all the Java files we have are things we wrote and use only the core Java libraries. So a couple things can go wrong here is if you have incompatible compiler and virtual machines. So if your virtual machine is older than your compiler, so if your virtual machine, say, was version 1.6 and your compiler was version 1.7, any code compiled in the 1.7 with a 1.7 compiler is not compatible with a 1.6 virtual machine. Kind of makes sense because if the language or features or have evolved from one to the next, there's things in the 1.7. The compiler makes assumptions in the 1.7 environment that the 1.6 virtual machine can't understand. And the other thing is dependencies on third-party libraries. This basically comes down to having the right class files when you go to run or compile. Anyway, so that's a subtle, the quick down and dirty difference between C++ and Java in terms of how you get from source code to applications, and a little bit on what it means when we say Java is a very portable language.